So let's dive a little deeper into the scientific method itself. Okay, we defined some terms, but what is the scientific method? Well, first of all, scientific method is humanity's most reliable avenue to knowledge. And that's through testing of falsifiable hypotheses via empirical and measurable evidence. That's a lot of long words. I get that. So the point here is science seeks out facts or objective truths by developing ideas, also known as hypotheses. So they develop these ideas, they put them to the test, they collect, they analyze data, and then they either throw out the wrong hypotheses, they run with the ones that are correct, or they redevelop the ideas or hypotheses based on their results and make them more accurate. The whole time, they're trying to avoid bias, and they account for as many outside variables as possible to make sure that they reach a reliable conclusion, whether or not it was their first idea. That doesn't matter. It doesn't matter whether the first idea was correct. It matters whether your results are consistent and realistic. Now, perhaps this will be a little clearer if we go through the process. These are the parts of the scientific method. Now, I don't call them steps because it's not a simple 1, 2, 3, 4, 5, 6, 7 process. Sometimes scientists will have to repeat steps. Maybe they identify the problem, do some research, create a hypothesis, but then they don't feel confident in it. So they go back and they do some more research. Okay. Typically, those scientists cannot skip any steps because this would invalidate their claims. It would mean they haven't done it appropriately. Their science is not valid. So, like I mentioned, we start off by identifying the problem. What do you need to figure out? What rule of nature are you trying to figure out? Here you are essentially writing down the question that you have. What's the next step? Test it? No. You see if someone already knows the answer, or a part of the answer, or just something that you need to know that'll help you out. And then you go from there, citing your sources appropriately. We call this researching and finding background information. Now, once you have the current knowledge available to you and an understanding of the current models associated with your idea, then you can make a claim. The claim we call a hypothesis, or this is the verb hypothesize. That's what you do. So you're probably thinking of the words educated guess. Stop right there. That's the old, well, not old, just younger version of hypothesis. It's not very nuanced. What I want you to do is write down the following in big bold letters, square, underline, box, star, whatever you need to do. Testable prediction. Any hypothesis must be testable. It must be falsifiable. If you can't prove it wrong, it's not a hypothesis. Also, a hypothesis predicts the outcomes of an experiment or a particular setup. That's how you determine whether it's right or wrong. Okay? So it has to be a testable prediction. And now here comes the fun part, right? The experiment. All right. Now, I think it's pretty fun, but it's also the place where attention to detail, patience, and discipline end up paying off. Now, in your hypothesis, you should have defined an independent and a dependent variable. In other words, you probably said something like, the thing X will have this effect on thing Y. For example, the stronger force with which I hit Mr. Dorsheimer, the further distance he will fall back. All right. So, the independent variable is the X. It's the force that I'm hitting Mr. Dorsheimer with. It's that thing that you are consciously changing, probably in particular increments, to see what effect it has on Y. This is the thing that you are changing on purpose to see what effect it has. And that means there's something that's dependent upon that independent variable, which is the dependent variable, right? That makes sense because the dependent variable is dependent upon something else. That's your Y. That's the thing that's affected by X. It's how far Mr. Dorsheimer falls back. It's the thing that you are ultimately measuring and comparing those measurements to the measurements when X had different values. But in any experiment, you can't just have variables and variables and variables. You have to keep some things the same. Those are what we call constants. A constant is a factor that stays the same no matter what. The only things that should change in your experiment are the independent and dependent variable. Here, Mr. Dorsheimer, I should be hitting him the same way each time, not his shoulder one time and his torso the other time. We also should, both of us, be in the same stance each time. We should be the same weight each time, under the same experimental conditions each time. If I don't keep things constant, I cannot claim that it was only the independent variable that affected the dependent variable. In other words, my experiment is worthless. Though, I did get to tackle Mr. Dorsheimer multiple times, so that's a win. Then we've got control. Now this is always a little tricky one. So the control is what would normally happen. It's more commonly used in social sciences, psychology, behavioral sciences, biology, medicine. The control is the results, what the independent or the dependent variable would be under normal conditions. It's something to compare to. If you were trying to figure out whether or not you should water your tomato garden more often or less often to grow more tomatoes, you have to establish how much water you give on a regular basis first. If you test some variables of watering frequency and you find that all of them give you fewer tomatoes than your control, the way you normally do it, if all the rest of those numbers are lower, well, then you know what you're already doing is best. But if you didn't run the control trial of regular watering and then you compared your results to that, well, you would conclude that some other watering plan is best, even though it's not. Then you have fewer tomatoes. Now lastly, the conclusion. Finally, you're done. You have your data. You've graphed it. Now what? You summarize the results. Now there are three options here. You can confirm your hypothesis. You can refute the hypothesis. Or it could be inconclusive. If you want to put that in Mythbusters terms, it's either confirmed, busted, or plausible. All of these categories refer back to your hypothesis. The data can confirm if your hypothesis is correct. It can refute your hypothesis by showing the opposite or some other effect than you predicted, or it doesn't really tell you either way. Perhaps your data wasn't clear, not well managed, or simply flawed. I hope we wrote down all the notes that were important to you, so make sure your notes are full and you have a question to ask.